It's not responding. Oh, okay. Okay, we're recording.
Okay.
It's a great pleasure to have Professor Hans Wenzl from UCSD to give a talk today. So Professor Wenzl works on subvector theory, representation theory, tensor categories, and low-dimensional topology, and he made a great contribution to these areas. So his topic today will be module categories for SUN at level K. Hans, please.
All right. Okay. Thank you for the invitation to give a talk here. So, all right. So, as you say here, what the title says, we want to classify module categories for SUN sub K. I will sort of explain what this is. So now there's an abstract classification of module categories has been achieved to a large extent now by work of Terry Gannon and Edie-Michell and others already before, but I think those are the ones who achieved sort of the most recent breakthroughs. And this is given by something called modular invariant, which is essentially certain matrices with integer coefficients. So this is mostly just a combinatorial problem. But then having this, there's still the problem of finding an explicit description of these module categories. And some of them were kind of mysterious. And again, I explain this in detail. And so basically the point of this talk is that for a large class of these module categories, we can use the combinatorics known for certain embeddings of Lie groups to describe this. Of course, it will not be the same, but it will be related. So that's the very rough outline. So let's get started with some general stuff here. So probably most of you or everyone here knows this, but let me just fix notation here. So we assume we have a nice tensor category. It should be semi-simple, rigid. Our home spaces are C vector spaces. So then a model category M of C is a C category with a function which are called tensor from M cross C to M, which satisfies the usual associativity conditions, which I am not going to write down, but which will not be that important here. So some of the examples here are just say you have two groups, H embedded in G. It should be finite or could be compact groups. Then we can make the representation category of the subgroup into a module category of the representation of the big group by a very simple method, namely by the restriction functor. So if we have a representation here of the subgroup M and a representation of the big group X, then the module action given here by this tensor sign is just given by the ordinary tensor product of H representations, where we tensor M with X viewed now as an H representation. So this is really a pretty easy example, but it will be it's a good model. And of course, coming from subvectors, there's also a standard example for embedding of type 2-1 factors, could also be type 3-1 factors or more general. So if we have this embedding, then we can form tensor powers M over N. So we take the nth tensor power of M by taking the tensor product of M over the subvector N. And so C then is just the category of N bimodules generated by such tensor powers. And the module category is the category of Mn bimodules. Obviously, we have left and right actions on this, guys. And so then we also have a very obvious right module action on this, because if we tensor an Mn bimodule by an Nn bimodule, we get again an n bimodule. So this is again a pretty, at least in principle, pretty easy example. So now how do we describe or classify such module categories? So one, of course, again, we have fusion rules, which is again is pretty straightforward. So for simplicity, we only assume that we have finally many irreducible modules in our module category, as well as in our tensor category, up to isomorphism. So then, of course, if I had tensor and MI, a simple module object with an object of the category, it decomposes into a direct sum of simple modules, and with multiplicities aij. And so then we can form from this an m by m matrix, AX, and this gives us a representation of the fusion ring of the big category, which is called a NIMRAP representation. So this essentially describes the fusion rules. And the probably deeper going thing is by using this description via algebra objects. So now again, an algebra object A in C in our tensor category K is just an object with two canonical morphisms. One is embedding of the trivial object into A. And so the trivial object is a direct summand of A. And we have a multiplication morphism from A tensor A into A. And of course, this should satisfy natural conditions, like this should be, the multiplication should be associative, which I wrote down here in the morphism. So if we have 3 copies of A, it doesn't matter whether we apply our multiplication map first to the first 2 copies or to the second and third copy, we get the same result. Similarly, we can define an A module, which is just an object Y in C, for which we can define an A action on it. And the A action is given again by a morphism from A tensor Y to Y, which again satisfies the usual associativity constraints. So basically, if you look at the lowest line, the obvious thing A1, A2 tensor Y should be the same as the right-hand side. And then you just write it out in terms of this maps, and then you get the identity in the line above. Okay, so this is all just some basic abstract nonsense. So now the important thing about this is that the theorem by Ostrich, that we can characterize a module category via categories of A modules. So that means we have this theorem here: for every module category M of C exists an algebra object A in C such that M is isomorphic to the category of A left modules. And so again, here we assume we have a right action on this. All right, so let's look at examples. So one is, okay, let's go back to our old example of M to be the representations of a subgroup. Then we have the what is the algebra object in this case? So we can pick as an algebra object the functions on the cosets of the left cosets of G mod H. So this is, so in this case, it's clear what is the multiplication. It's just multiplication, the ordinary way how we multiply functions, just by pointwise multiplication. So the usual multiplication for functions. All right. Now, of course, we would also like to know how this looks like as a C object. And so it's known that this is just given, the algebra A as a G module is just given by inducing the trivial representation of H up to the big group. So let's see, like, for instance, for our first example, say, let's take a subgroup HS2 and a big group S3, symmetric groups. Then A would be given as a direct sum of the trivial and the two-dimensional representation. And you also see, if you add up the dimensions, you get 3, which is the index of S2 in S3. Now, the same could sort of go also for infinite groups. Also, I mean, this would be more complicated. And I just write down this example here because it will be important later for describing our module categories for fusion categories. So let's take for H the orthogonal group, and for G the unitary group, group of dimension n. So unitary n by n matrices here the orthogonal n by n matrices. So then this is an old result, which I think goes back to maybe Littlewood. So if you induces up the trivial representation to G, then this is a direct sum of irreducible representations of UN labeled by Young diagrams, lambda, with the following two properties. On the one hand, lambda here should have at most n rows. And the other thing is that each row has only an even number of boxes. So that's the combinatorial result. So okay, I mean, one could also state the other way around. These are all the representations which restrict the orthogonal group contain the trivial representation as a sub-representation. Okay, so this is a combinatorial result, which is coming from representation theory. So in principle, one can calculate this. Another example would be that let's go back to our subfactor example, where M is the category of Mn bimodules for n and m. So then the algebra object is the most obvious thing one could think of, namely it's the big factor viewed as an nn bimodule. So this is again an algebra object. And again, it's clear what the multiplication here is. It's just M is an algebra, so we have a natural multiplication map in our algebra, which is also an n bimodule map. So this would be two simple examples for algebras. All right. So these are quite general results. So we now want to concentrate to a special class of tensor categories called modular tensor categories and modular invariants. Okay, I'm not going to write down all the axioms for a modular tensor category. It has a braiding in particular. It has many nice properties. It's semi-simple. It's rigid. So what we need here is the following. So C is semi-simple, and it has finitely many irreducible representations of irreducible objects. And so we fix here a label set lambda, which labels this the irreducible objects up to isomorphism. So then, having this, we can form a vector space whose basis is labeled by this index set. So we have as many, so the dimension of this vector space is equal to the number of irreducible objects up to isomorphism. And then the property what we are interested in, and which gave it the name modular tensor category, is that a modular tensor category allows a canonical representation of the modular group SL2Z on this vector space. So of course, these are the 2x2 matrices with coefficients, with integer coefficients and determinant equal to 1. Okay, so we have this representation. So we now can define what is a modular invariant. A modular invariant M is again a lambda cross lambda matrix. So I mean such that M commutes with SL2Z, with the SL2Z representation, and all entries of M are non-integer, are non-negative integers. And moreover, it's normalized such that it's 0, 0 entry, which is the 0 is the label for the trivial representation, so that it's 0, 0 entry is equal to 1. So then the theorem which we are going to use is now that if we have, if M is a module category of a modular category, then we obtain a canonical modular invariant M. And also I have outlined here how does one calculate this matrix M, which I don't know. This may be, I'm sure this is known to at least some people here, but let me just briefly say, how does one obtain this matrix M? So there is a canonical way. Okay, I wrote it down here. M lambda mu is the dimension of the Hom space of two AA bimodules, alpha, which alpha plus x lambda and alpha minus x mu. Okay, let me briefly outline this, how are they obtained. So, okay, given an object X in our category C, we want to construct an AA bimodule. So what we do first, we tensor this with A. So this makes it obviously into an A left module, where the left action is just given via the multiplication morphism for A. We can also make it into an A right module, alpha plus X, essentially by using the braiding, which moves the A to the other side. And so I wrote it out here. So alpha plus X tensor X. This is isomorphic, as I see, object to A tensor X tensor A. So then, using the braiding morphism, we can interchange this. So we can move A and X, such that we can now apply our multiplication map. And so we get then back A tensor X, which is isomorphic to our alpha plus X. Now, because of braiding, we have two possibilities how to do this. We can either take this braiding here, which I drew as a picture here on the last line here, or we can use the opposite braiding here. And so we get two objects which may or may not be isomorphic. So in general, they are not isomorphic. And so hence we And so now, hence, now the entry of the M is given via this home space. All right, so what's the point of all of this? So if you have a modular tensor category, to classify modular categories, we first have to look at what are all possible modular invariants of C. All right. So now let's, after all this abstract nonsense, let's turn now to some concrete examples. So we look at this modular categories SUN sub K, the fusion categories. So they can be fairly easily described as follows. So the simple objects X lambda are labeled by Young diagrams with with at most n-1 rows, and such that lambda 1 is the first row is has at most k boxes. So basically, these are all Young diagrams which fit into a rectangle with side lengths n-1 and k. Then usually the object would correspond to the vector representation. Sn is usually then given by the one box Young diagram. And so we get the following tensor product rules as written here. So if I have an object labeled by a simple object labeled by the diagram lambda, and I tensor it with X, the element corresponding to the vector representation, I get a direct sum of objects labeled by Young diagrams mu, which can obtain by adding a box to lambda. Now we are also allowed to add a box in the nth row, which then would correspond to the diagram where we remove the leftmost column. So you can see it written out here. So in this line below this formula. So then it was shown in an old paper that essentially one can classify all this tensor categories with these fusion rules. So they're classified by Q, which is a primitive n plus kth root of unity, and theta, which is an nth root of unity. Basically, the theta corresponds to a twist of the associator via a 3 cocycle of Z mod n, but this will not be important here. All right, let's then let's do two examples in greater detail. First, for n equals 2, the objects are given by the one row Young diagrams going from the empty one to the k to the Young diagram with k boxes. This and the tensor product rules are just given by this formula here. So it contains at most 2 objects, and graphically can be described just, if you form a graph with the AN graph, or I guess it should be here a k+1 graph, then if you tensor the object labeled by M, then it's a direct sum of its 2 neighbors. What are the modular invariants here? This was essentially already, the modular categories were essentially already classified in an old paper by Goodman, De La Harpe, Jones, without using that notation. And so we have what I would call the non-exceptional ones, because they appear for infinitely many Ks. The one is, of course, is the identity matrix, which is obviously a modular invariant. And the other one is I plus T, where T is the reflection in the middle of this AM-1 graph, which you'll see here indicated. And this only works if k is even, but again, this will not be so important. And also, there are 3 exceptional modular invariants corresponding to the graphs E6, E7, and E8, which are at level, let's see, 10, 16, and 28. And the numbers are a little bit nicer if you add the rank of it. So 2, then it's 12, 18, and 30. And so I only wrote down here as an example the modular invariant in the E6 case, so where it is the modular invariant is given by t plus t squared, where t is a permutation matrix, or which interchanges the trivial object with 6, the object labeled by 4 with 10, and the object labeled by 3 with 7. So it's, well, okay, it's actually not a permutation matrix because it maps some objects to 0, like 1 is mapped to 0. So the main point here is actually now we are talking mostly here about the non-exceptional ones. So let's look at what does it look for n equals 3. So there the objects are labeled by Young diagrams with 2 rows and at most k boxes in each row. So you can arrange them here in a sort of like Pascal triangle here. So this goes down to the diagram with k boxes in the first and second row. And also the tensor Berkeley rule can be nicely described graphically as via this graph here. So basically, if we want to tensor a representation here, then we just we put it into this Pascal triangle, add all these arrows here, and we write down whatever is allowed to exist, which is in this triangle. So here's an example: x, the 2-row thing tensor with x. You can go down to the left, you can go to the right, but you cannot go up because there's nothing up there. So we get this. Okay. So what are the modular invariants here? So we already see here some, this has some nice symmetries here, this triangle. And so the non-exceptional ones are closely related to these symmetries. Namely, one can show that one of them is related to the rotations by 120 degrees. So, which one cannot, this can be achieved by tensoring via the object here in this left down corner. This is again an invertible object, so it's so it permutes this object, and it corresponds to a 120-degree permutation. Using so this is one symmetry. The other symmetry is the reflection in the middle of the axis here. So if we draw a vertical axis here in this triangle, and we reflect about this, this also gives us a matrix, and this matrix corresponds to mapping an object to its dual object. Now, using this, guys, we can get 4 non-exceptional modular invariants. So one is, of course, the identity. Then the second one, which I call O, is just we average over the rotations. So the identity plus rotation plus t squared. Then I call, we have C, the reflection at the central vertical axis. I use C because this is usually called charge conjugation in the physics literature. And of course, if O and C commute with the M2 action, then also CO commutes. And it's not hard to check that also this satisfies the condition that the 0, entry is 1. Okay, so these are 4 infinite series. So they work essentially for infinitely many k's. I mean, so essentially the charge conjugation works for all k, and I forgot now whether there's any condition on k for the rotation, but I don't think there is. So I think they all act for all possible k's. They work. Okay, fine. So we have this, but so now the problem now is, what does it say about our module category? What can we say about the corresponding module category? And a priori, I don't think there's even a general theorem which tells us that such module categories always exist for every module invariant. Also, I think this has been, it's true now for SUNK, which I think Kane and Edie-Michell checked this. All right, so the question is, describe the corresponding module categories, and determine the fusion rules, and determine some algebra object which would describe this. Of course, I mean, if M is a trivial modular invariant, this is easy, because then this is just the category itself, viewed as a module over itself. So this is no big deal. What about if M is O? I used O for something called orbifold. Here, the algebra is just the sum of the ends of our AN graph. So it's the trivial plus the last allowed representation, which is again a dimension 1, an invertible object. So A essentially corresponds to Z mod 2. And for n equals 3, it's just the algebra would be the direct sum of the 3 corners of our triangle here. So there's this and this. And here this algebra would correspond to Z mod 3. And essentially the objects correspond to orbits under these group actions. So for M equals O, these are well understood. So the question is, what about C and CO? So now, back like a long time ago, like more than 10 years ago, I had quite a naive idea of how to find module categories without really knowing about this stuff, which I should have, but I didn't. So essentially, I proved there exists module categories for S, U, and K, and there are some technical conditions. So here K should be even with an algebra which labeled by a direct sum of X lambdas, where lambda are in the labeling set, satisfying that 2 divides the number of boxes in each row. And an additional condition was also that the number of boxes everywhere of the whole Young diagram should be divisible by n. Now, this looks kind of familiar to this example which I wrote at the beginning, namely that 2 has to divide the number of boxes in each row. This appeared also exactly in, let's see, where did we have it? Yeah, sorry. For the example with here. Yeah, this condition that 2 divides the number of boxes in each row appeared also in this induction in the algebra for the model category corresponding to the subgroup ON of UN. So this should be related. And in some sense, it's not surprising because I will tell a little bit later how I got to this thing. So we see here that the algebra, where is it? Yeah, the algebra constructed here could be viewed as a kind of fusion version of the algebra coming from the subgroup ON into UN, or one could also say SON into SUN, but that's don't worry too much about the combinatorics. Similarly, if N is even and K is arbitrary, one actually gets a second algebra where now, again, N has to divide the number of boxes of the Young diagram, and now 2 has to divide the number of boxes in each column. So it's kind of like a transposed version. And this corresponds to the restriction of the UN to the symplectic group. But again, this will not be so important here because I don't want to talk about all possible examples. Okay. So now for n equals, so this was true, I guess, for pretty general, for, as I said here, and the part 1 was true, showed for arbitrary big N, and part 2 was shown for arbitrary big N even. Okay, now for n equals 3, this results were also obtained later by Evans and Pugh. And moreover, they also found the algebras for n equals 3 and k odd. Now, if you look at this here, that our case here in part 1, we had to assume k even. So they obtained a complete description of all possible algebras of model categories, even for exceptional ones, about which I will not talk here. And so in their case, so for k equals even, I already said what the result is. So this would be the result I obtained is here on the right upper corner here, model invariant for CO. And so Evans and Pugh also obtained this for k even. Let me see, what did I write? Oh, for k odd. And for k odd, the algebra is in some sense even easier, because the algebra is just the direct sum of all irreducible objects in this. So, and so what you observe here also there, if you look at these two columns, then they are almost the same. The only reason is on the rightmost column, this is a subset of the Young diagrams on the leftmost on the left column, and the condition is that here are only Young diagrams allowed whose boxes are divisible by 3. So this is, in some sense, you could view this parallel to this orbifold and trivial case. So and in any case, so we have a complete description of of this module of the algebras for module categories in this case. All right, so some observations here. Okay, the first one is already this, what I already said essentially, that the algebras here can be viewed, the algebras here in this fusion category case can be viewed as truncations or of algebras which appear from natural embeddings of orthogonal groups into unitary groups. And part 2 is also what I already said. Okay, now what about in the other cases? So in this lower case, where the algebras allows everyone, you could not, oh, sorry, let me do this again. Now, for the odd case here, originally there was no interpretation in terms of an embedding of Lie groups. However, but in a more recent work, which will appear in 2023, and so we considered the inclusion of the symplectic group n-1 into SUN for n odd. And so then one could show in this case that this embedding SPn-1 into SUN also allows a Q deformation. And so hence it allows a module category of the quantum group, which is a deformation of this embedding here. Now for n equals 3, one can show that this corresponds to the case for Q, a certain root of unity, where one mods out via negligible objects. So it is expected that this will also work for other n odds, and that we can get module categories also in the fusion case. So this, unfortunately, seems to be a little trickier than the other cases to prove this thing, and I got kind of a little distracted by other stuff. So this hasn't been checked yet for n bigger than 3 odd. Now, I had the fortune that Edie-Michell was visiting at San Diego for a year, and so I learned about his work, where he has classified module categories S, U, and K. And so essentially, he can show that this given by this module invariance, and also using results of Terry Gannon, can get a complete classification for n less equal than 7. And and also he can classify what are all this what they call non-exceptional invariants, modular invariants. So now essentially all this non-exceptional modular invariants can be realized as truncations of embeddings of certain Lie groups. And so I have, so let me first say, where is this? Yeah, sorry. I mean, I wished I could have written this a little bit nicer, but I ran out of space. So let's go over Keynes' result slowly. So roughly speaking, we look at all divisors of D of our n, of SUN. For each divisor D, one obtains 2 modular invariants. One of them is an orbifold, which is easy to describe. It's an orbifold. Yeah, so I wrote it down here. if you look at this corner here, it's an orbifold with respect to the subgroup of Z mod n of order D. And also the algebra is fairly easy to describe. It's essentially given by the objects, a direct sum of the objects corresponding to this subgroup. The second one, it would correspond to the CO, which we had. And this is given again by those x lambdas, where the set lambda is given by this inducing up from H to SUN, where H is a subgroup, and the number of Young diagrams are divisible by D. So this is a very nice, I think, in my opinion, and also I think in Kane's opinion, this would be a very nice result, which we think is true in general. And let me just write down here in this table. So for which cases do we have to choose which subgroup? So if n is even k even, you take ON into SUN or SPN into SUN. So there are two possibilities. There's actually one extra module category. So that's, if n is even, k is odd, then we take the symplectic group embedded into SUN. If n is odd and k is even, we take SON into SUN, and n odd, k odd, we take this inclusion here. So, yeah, so in some sense, we can, if our conjecture is true, and it has been proved in a number of cases now, we would have a very nice, I think, conceptual description of all this algebras. And okay, so this would be basically the result, or rather conjecturally. So the result has been proved for the n even, k even, and for d equals n. So that would be a case. And yes, anyway, if someone is interested, I'm happy to tell him exactly which cases are proved and which are not proved. All right. So maybe a little bit about proof. As I said, the method is kind of old. This is already what I used like 10 years ago. So let me briefly, somewhat vaguely indicate how this goes. So we start out here with, so we pick our subgroup H according to this table here. And we take V to be the n-dimensional representation of SUN. So then we look at the endomorphism space, the commutant on V tensor n of the SUN action, which of course is embedded into the commutant of the subgroup. The Q deformation of this is well known. We get this one, which is given by the Hecke algebra. And yeah, I think I will write down the relation stuff below. So what we need is, we want to construct an algebra DNQ, which is a deformation of our n sub h, V tensor n, and which contains the Hecke algebra. Now, of course, so what are the relations? Now, this is again where the subfactor background comes in handily, because for subfactors, if one wants to construct subfactors, one always wants to have the commuting square condition. So we also go for this here. So we already know that the Hecke algebras have a canonical trace called the Markov trace. So we want to define an extension of this Markov trace to this DNQ, which satisfies the commuting square condition. Now, commuting square condition just means a trace functional that induces a bilinear form on this algebras, and commuting square condition just means that projection onto the upper right corner and the lower left corner, that means the two intermediate algebras, that the projection onto this should commute. So essentially, and the amazing thing here is that for these cases we consider, this really already pins down the relations for these extensions. So let me make it a little bit more concrete. Let me see where I have it here. So yeah, so we want to find this algebra D and Q, which should contain the Hecker algebra H and Q. And it should be a Q deformation for the centralizer algebras of ON into SUN. So then we know in the classical case, Q equals 1, we only need to add one more generator to these generators of the symmetric group. So now the generators of the symmetric group become the generators of the Hecker algebra. So G1, G2, Gn-1 satisfy the Hecker algebra relations, which I wrote down here like this. So you satisfy a quadratic equation, and they satisfy the braid relations, where Gi would correspond to this crossing here. Now, similarly as in the classical case, the E is essentially a projection. It's E squared is equal NE, where N is the Q number for N. And E should commute with the first one, namely E is essentially just the subprojection of the eigenprojection for Q. E commutes with generators of index bigger than 2, and for E equals G2, it satisfies this relation. So this is all pretty straightforward. Now the kind of mysterious relation is now this relation 4, which yeah, and I think I will have to go back to this, because I think in order to prove these missing cases, I think I probably need to understand these relations a little bit better. So essentially, often a pictorial calculus would be helpful. Unfortunately here, one has to be careful, because it doesn't work in general. Okay, for E, the symbol would be this one here, because that comes already from the classical Brauer algebra. So E, one could take a symbol, this one. So then, what I wrote down here, this relation here, G2, G3, G1 inverse, G2 inverse, is essentially given here by this lower part of this graph here. So without this upper E. And so if you then multiply this again with an E, then we can identify this with this symbol, and one can show that this is indeed, if you square this guy, then you get n squared times the same thing. So this would be fine. However, when you change the braids a little bit like this, you will get something different. So in that sense, I mean, and I think there's still something missing here to get a better understanding, but it would be nice, I mean, if one could get some kind of whatever planar description or yeah, some more conceptual description of this. But anyway, I was already planning to look at this again, and I wished I would have had more time to maybe finding something a little bit more conceptual. But it turns out anyway that these relations really define the Q deformation of which we want. And one can use this and to also construct subfactors and module categories. Okay, so this was this case for ON into SUN. All right, so I skipped that to get to this thing. So let's just wrap it up. So so we have now defined our D and Q. So then how do we construct the module category of our fusion category? This is again pretty straightforward. Essentially, so the objects of our M are just the idempotents of D and Q modulo modulo negligible morphism, or here modulo the ideal, which is given by the annihilator ideal of the trace. But anyway, it's just the morphisms coming from D and Q modulo negligible morphism. And of course, the fusion category SU and K can be constructed from the Hecke algebra, again, modulo annihilator, modulo negligible morphisms. And so then the embedding, so obviously HN is a subalgebra of HN, and so which gives us also canonical embeddings for dm tensor HN into 2m plus n. And so hence this will define the model action, because if here we have an object of E of the model category, F is an object of our category, then E tensor F is again an idempotent in this bigger algebra, which corresponds to an object in our model category. All right. So as I already said before, so we expect to get concrete descriptions for all non-exceptional modular invariants for SUN, and again they have the form OD, which is the orbifold, with respect to D, the COD for any divisor D modulo n. I mean, again, I threw a few subtleties under the carpet here, but this is roughly speaking what it is. I mean, for n even, there's a little bit more, but I'll leave it like this for the time being. I guess I talked a lot about now here this non-exceptional model categories, so I should probably say also a little bit about the exceptional ones. So the biggest source of exceptional model categories comes from something called conformal inclusions. So, and this was discovered by Fang Xu, and which I think, yeah, but so in principle, a lot of the combinatorics is known, but I still don't think that there is a general description of, say, the algebras of this, but it is known each conformal inclusion gives one. And yeah, if there's interest, I can explain what this exactly means. It has to do with representations of loop groups. There also exists another construction of exceptional module categories via planar algebras, like Tsinghua constructed some of them using in his paper Young-Baxter relation planar algebras. And this is essentially, I mean, in principle, almost the same. The idea is more or less similar to mine, namely he constructs extension of the Hecke algebras by a completely different method, and then shows that this again gives module categories. So and these are related to some of the conformal inclusions. So finally, there also exists some other exception module categories which don't seem to come from conformal inclusions or planar algebra, at least not so far known. I think I probably wanted to write conformal inclusions instead of planar algebra. So sorry, that's a misprint. And so they were found by Terry Gannon, by Edie-Michell, and so I think Terry used some vertex operator algebra results for some of the results for some of these exception module categories. But in general, I mean, there are only finally many exception module categories exist for each S, U, and K, and this is again some recent results by I think Andrew Chopire and Terry Gannon. So, all right, so I think I'll leave it with this. So, okay, thanks for your attention. So, okay, maybe I finished a little bit earlier, so sorry, but I'm happy to answer questions.